Hello everyone. Okay, so in this session I'm going to demonstrate on an example that deal with the UDL load. Okay, so what you can see in these examples, we have a simply supported beam that loaded by the 4 kN per meter UDL load. Okay, so in the previous example we have deal with the point load, and we have seen how we can develop the ILD for the shear force, bending moment, and direction and support. But here, what you can see here, we have a UDL load, and in these examples, I'm going to demonstrate how we can develop the ILD and how we can apply this particular ILD in order to find the critical value in the problem. Okay, so let's look in detail on this example. So basically, we have a simply supported beam that loaded by the 4 kN per meter UDL load. Okay, so in these examples, we need to determine the maximum positive shear at a point C and also the maximum positive moment at a point C. Okay, so we will go to part, which is the first part is to develop the ILD for the beam. Another part, we will apply the ILD diagram to determine those value of maximum positive shear and the moment at a point C. Okay, let's go for the first part. Okay, so this is the solution of first part, where you can see that the equations of influence line diagram has been established in this slide. Okay, let's look how we can establish that particular equation. Okay, so this is the original diagram from the equation. So this is the UDL load, the actual load. Okay, so in order to develop the ILD diagram, you need to remove this particular actual load as what you have done in the previous example. So you need to remove all the actual load, and then you need to put the one unique load on the diagram. Okay, so since the UDL load, since we deal with the UDL loads, you need to place 1 kN per meter UDL load. Okay, so the length of load is 1 meter. That's on the actual load. The length of UDL load is 3 meter. So you need to change from this to this particular condition. Okay, so based on this particular diagram of UDL load, okay, so you can decide which diagram that you want to use in order to find out the equation of a shear force and the bending moment. Okay, so since the point C is our objective, so you may to consider whether the diagram left hand side of the point C or the right hand side of the point C. So based on this solution that you can see in this slide, the rigid diagram that has been considered is the left hand side of a point C. Okay, so here is a UDL load. Okay, so based on the load that has been put within a AC. Okay, so meanwhile, this is the condition where the load is moved in within a CB. Okay, so what you can see in between both of this diagram, so the diagram remained on the AC. Okay, so actually the basic principle of ILD based on the previous examples still remain the same. Okay, but here you need to be careful with the load applied. So if the questions consider the point loads, you need to apply 1 unit load, 1 point load, 1 kN load. If your load is about the UDL, so you need to apply 1 unit load of UDL. Okay, so based on this diagram, you can see that the direction is equal to 10 minus x over 10. Where this particular step is not shown in the slide. So I hope that you can figure out yourself how to get this particular direction support. Okay, so and we have internal moment here and shear force at the point C. So based on this free body diagram, okay, so you can see that the equation of shear force and bending moment is given by this equation. Okay, so this for AC. So meanwhile, in CB, so the UDL has moved beyond the point C. So and UDL load is no longer available in this diagram, which is along the AC. So based on this diagram, free body diagram, we can figure out the equation of a shear force and bending moment without the availability of this particular UDL. Okay, so we have two set of equations. Okay, so of a shear force and the bending moment, and you can proceed to plot the ILD diagram for shear force and the bending moment. Okay, so this is ILD for the shear force, and this is ILD for the bending moment based on the value that you can calculate it based on the equation that you have determined in the previous slide. Okay, so I want to explain in detail how to get this value in the table and how to plot this. So, and the next step, we will look how we can use the diagrams in order to calculate the value of maximum shear force and the maximum bending moment in the problem. Okay, so let's look on the shear force. Okay, so we know that the actual load imposed on the beam is UDL load, which is equal to 4 kN per meter. So since the question asking about the maximum positive shear at C, so you need to position this particular UDL so that you can get the maximum value of a shear force. Okay, so we know, okay, by looking on this diagram, we can see that this is a negative region, this is a positive region. For sure, you need to place this particular UDL in this manner, what you can see in the slide. Okay, so these positions will give the maximum value of a shear force point C. Okay, so how to calculate the value of shear force? So basically the equation is you need to use this equation, which is UDL multiplied by the area under the influence line diagram for BC. So where UDL value is equal to 4 kN per meter. So the area below of this diagram can be seen here, which is in a blue color, the shaded area in a blue color. So the shape of this area is trapezoidal. So based on the trapezoidal equation area, so you can determine the area of this particular shaded area and multiply with 4, and you can see that the maximum shear force at point C is equal to 5.4 kN. Okay, so that's it for the shear force. So we have done to get the value of maximum shear force at point C. Let's move on the bending moment. Okay, so for the bending moment, it's quite tricky. So you can see that they have three possibilities that can give the value of maximum bending moment for the problem. That means that the maximum positive value for the problem. So by looking on the diagram, so you can see that the entire diagram is positive. Okay, so let's look on the option here, the possibility. Okay, the first possibility is based on this position, where all the diagrams of all the length of UDL is to the left of a peak point. Okay, so meanwhile, the second possibility is you can see that this UDL, some length is to the left, some length is to the right of a peak point, and the third possibility, you can see that the entire length of UDL is to the right hand side of the peak point. Okay, so this is a peak point. Okay, so to calculate the value of a bending moment, so the same equation, so you need to multiply the UDL value, which is a 4 kN per meter, multiply with the area under IL diagram. Okay, so for the option 1 and option 3 is obvious, so you can simply find out. Okay, okay, for instance, for the option 1, the first possibility, so you can see that this particular value of moment can be obtained by multiply the value of UDL with these regions in yellow color. Okay, so this give MC equal to 18 kilonewton meter. Okay, so and the third possibility is you can multiply the UDL value with the area in a blue region color. Okay, so this trapezoidal shape. So by that, you can see that the MC is equal to 21.6 kN meter. Okay, so and how about the second possibility? Okay, so we know that 18 is for the first possibility. The third possibility give 21.6. So we need to compare all this value and choose the highest one. So the highest one will be the answer for maximum positive moment for the problem. Okay, so to discuss in detail on this particular second possibility, so let's move on the next slide. Okay, so this is the diagram that I'm going to use to explain how we can determine the maximum area for trapezoidal shape. Okay, so by looking on this diagram, you can see that we assume that we assume the variables value here, which is x value, is a length of it is the UDL length to the left. So and the right hand side will be 3 minus x. We know that the total length of this UDL is 3 meter. So this will be 3 minus x. Okay, so you know that this x and this is 3 minus x, and our objective is to find out this particular x. And for the verticals direction, so you can see that this is the we denote this particular height is equal to y. Okay, so we wanted to find the value of x and y in order to get the maximum area of a trapezoidal shape. Okay, so how to get the value of x and y? So we will use the mathematics. Okay, so since we deal with the two variable, two unknown, so we need to come out with two equation to solve two unknown here. Okay, how to get the value of x and y? Okay, let's discuss in detail on this. Okay, so if you're looking on this particular diagram, okay, let's consider the left hand side of a peak point of diagram, which is this trapezoidal. Okay, so by looking on the left hand side of this peak point, which is this triangle, so actually you can see they have two triangle. So this is the first triangle, so and this is a second triangle. Okay, so basically you can solve for the x and y value by using this triangle. Okay, so and the first equation can be obtained from the ratio between the triangle here. Okay, for instance here y over 4 minus x is come from this this triangle. Okay, y over 4 minus x. So equate this particular slope. Yes, basically the y over 4 minus x is a slope. Okay, so equate this slope with the big triangle, this one. So which is the height is 2.4. So the base is 4 meter. So actually, if you have the value of y and x, so this will this value at the left hand side of equation will equal to the value in the right hand side of the equation. Okay, so simplify this, you can see that this is a first equation, which is y equal to 0.6 multiplied with 4 minus x. Okay, so do the same thing for the right hand side of the peak point. So the at the right hand side of the peak point, you can see that we have two triangle also. So this is a big one, so this is a smaller one. Okay, so by looking on this diagram, you can see that y over 3 plus x is come from this triangle. Okay, so the height over the base, so equal to the this big triangle, which is a 2.4 this height divided by 6 meter. Okay, so this actually the slope for this both of this triangle is similar. Okay, so based on that, you can see that the equation is equal to y equal to 0.4 multiplied by 3 plus x. So this will give the second equation. Okay, so we have two equations, and by that we can solve two unknown, which is referred to x and y, and the value is equal to x equal to 1.2 meter, y equal to 1.68 meter. So we have the value of x and y. So by that we can calculate the area of the shaded area, or the area of a trapezoidal, by using this equation. Okay, so the same equation. Okay, so by looking on the solution, you can see that the area of trapezoidal is given by this, multiplied with the UDL load, and simplified, you can see that the value of moment is equal to 24.48 kN/meter. Okay, so Thus, we compare this value with the first and third option. I mean the first and third possibility. Okay, so we have seen that this is a 18 kilonewton per meter for the first possibility and 21.6 is for the third possibility. And obviously you can see that this will be the answer for this particular problem. So the second possibility is the answer for the maximum positive value of a bending moment for this problem. Okay, so that's it for the session. So thank you for listening. See you in the next lecture.